Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Muchas gracias, Sergio. Bueno, bienvenidos nuevamente. Es un placer ver a todos ustedes acá, iniciando la 9ª edición del Microsoft Research Latin American Faculty Summit en este año, nuevamente en Viña del Mar. Nos reencontramos con Viña porque tuvimos el primer evento acá en Chile 7 años atrás, en el 2007. Bueno, ahora sí vamos a empezar ya la agenda de presentaciones académicas y de investigación. Para mí es un gran placer presentar al doctor Tony Hay. El doctor Tony Hay es vicepresidente de Microsoft Research. Él es responsable por todas las colaboraciones con universidades y centros de investigación a nivel mundial. También el doctor Hay es responsable por el grupo de investigación multidisciplinaria eScience dentro de Microsoft Research. Antes de unirse a Microsoft Research, Tony Hay también estuvo como director de la iniciativa de eScience, fue el director y creador de la iniciativa de eScience en el Reino Unido. A través de dicha iniciativa, el doctor Hay construyó una nueva infraestructura científica para investigación multidisciplinaria, colaborativa, muy intensiva en datos. También en la parte académica, el doctor Tony Hay fue decano de Ingeniería y de Ciencia Aplicada en la Universidad de Southampton. Les pediría por favor que me acompañen dando la bienvenida al doctor Tony Hay, vicepresidente de Microsoft Research.
Thank you very much, Jaime. So it's great to be back in Viña del Mar, and I'm hoping that my clicker will work. Yes. So welcome, yes, and it's great to be back here, as I said. So just so I give you some numbers to show that actually it's a rather impressive gathering we have here. A very distinguished audience of researchers and graduate students from 70 institutions, 50 presenters, which includes not only Microsoft researchers, but also researchers from universities in many of these countries, including Latin America and, of course, Chile, and altogether 14 countries. So what does Microsoft Research do? Microsoft Research is a very small part of Microsoft in total. It's around 1,000 people, and we now have well over 100,000 people employed in Microsoft with the addition of Nokia. And our role is unique in Microsoft in that Microsoft Research is absolutely intended to expand the state of the art in the areas where we do computing research, not every area, but in areas that are exciting and likely to lead to really innovations in products. Secondly, I was in the university for 25 years, but it's really very satisfying for researchers in Microsoft to be able to take their research and see their research actually appear in products that are used by millions of people around the world. So it's a particularly exciting time for researchers in Microsoft because we are now challenged to produce ever more exciting projects, and the pace of change seems to get faster and faster. And I think that the role of Microsoft Research will become really important for giving Microsoft an edge in innovation. And lastly, because we do long-term research, our role is to see over the future, over the horizon, and to make sure that we understand where the technology is going, and to make sure that Microsoft can respond appropriately, and also to make sure that we can answer some of the challenges facing the world and humanity in health, in environment, and also in education, as you heard from the Minister today. So Microsoft Research is a really exciting and very important part of Microsoft, even though it's only around 1,000 researchers. So, I talked about a golden era for computer science research in my opening remarks. And I do think we're at a very dramatic time in the history of computing. We're approaching the end of Moore's law. We've been used for the last 30-odd years for computing to get cheaper and faster and smaller. And that is going to come to an end when we get down to dimensions which are comparable to atoms. And that's not far away. And so what will happen to the IT industry? How will it evolve? Will the technology switch from silicon to carbon or DNA or quantum computing? Very exciting things, and Microsoft Research is working on all of those. Also, we see now the construction by many companies, including Microsoft, of these very large data centers with hundreds of thousands of computer cores in there. And actually, these computing and storage facilities, can we do things much more energy efficiently? Can we actually save energy, use the environment, the energy from water, from the sun, and so on, to make our data centers more efficient? And that's driving a lot of interest in new ways of powering data centers and computers more efficiently. And what is very exciting is that I talked about the fact that we're on the edge of solving some of these long-standing problems in artificial intelligence, computers that see, hear, and understand in the way that humans can. So sensors to capture people's voice and gestures. We all know about the Kinect sensor for Xbox, which captures gestures, and you can play games without a controller. That was actually a result of combined research in Microsoft research laboratories with the Xbox team to come up with a really innovative way of using gestures to control games. And there's been very exciting progress in natural language processing and in the advances of machine learning made possible by scaling up the machine learning algorithms, which we knew, up to new levels. And in particular, deep neural networks, this is a technology, one of the batteries of machine learning techniques, are now producing performance levels which are close to humans for speech recognition and for image labeling and classification. And that really makes a great deal of difference. And we'll soon see on your mobile phone, which of course in my case is not an iPhone, this is a Windows phone, and I won't talk to Siri, I'll be talking to Cortana, and that is a technology, an intelligent personal assistant based on Master Chief in Halo, of course, as you know, but it also uses these advances in machine learning technologies which were pioneered in Microsoft Research. And one of the areas that's important to me and exciting to me is that computer science is now actually driving scientists to understand challenges in healthcare, in genomics, in education, in environment, and so on. So these are particularly exciting things, and we'll hear about some of these exciting projects here, and we'll also hear about machine learning and in a session today, which I look forward to. So, what's the future of computing? Well, actually, the future of computing is you, all right? So these are some of the numbers that Microsoft Research has touched over the years. We've seen an example of an award to a graduate fellowship, and that's one of these examples here, but there's many other large numbers. This is, we have Anandan from our India lab with Vidya, who also organizes a very large symposium for young people with over 1,500 people. And similarly in China, we have large events where we get large numbers of students and we try and excite them into what's coming, what a role they can play. Because the future is actually going to be controlled by the people here, the young people who are turned on and excited by what they can do with the technologies. So I won't go through all the numbers, but you can see them there. We talked about graduate fellowships, but we have a program for faculty fellows. These are young academics who've just started their academic career, and this is a very prestigious. We give a very small number of these each year, and we give them a significant sum of money to enable them to get started in their research, to hire research assistants, graduate students, equipment, and so on. They can do what they like with the money. And this is, I'm pleased to announce, Professor Diego Fernandez-Slechak from University of Buenos Aires, and he's actually looking at computational characterization of mental states, which, if I'm sure some of you will remember, was one of the original motivations for the Turing model by Alan Turing, who then went on to consider artificial intelligence. And another faculty fellow from Microsoft was Louis van Ahn, who's now at Carnegie Mellon University. And he's the man who invented these very annoying things, these captchas, where you have to decide what these squiggly characters are. And so putting those together is one of the goals of Diego. So we talked also about the PhD fellows. We have Rodrigo Castellano from the University of Buenos Aires, looking at abstractions for people's behavior, and Carolina, who we just met, who's looking at human-computer interfaces in the area of healthcare, which of course has enormous potential for implications for a nation's health. And so a very exciting set of projects, and we wish them well in their careers. And another activity that we've been doing for 7 years now in Latin America is this Latin American and Caribbean Collaborative Research Institute, LACCIA, which is organized as a hub, which is in Santiago in Chile, and spokes in universities in the countries around. This was initially supported with a grant of $3 million from Microsoft, but it's been supplemented by grants from other organizations, the IADB and OAS, who actually, and also the partnerships with CONICET and so on, Colciencias and FAPESPI, who've also added to this. And so this has meant that there are collaborative projects between researchers in Latin America, and so far in these years, there are about 5 or 6 of these a year, and there have been 32 of them, and 14 of those have been research projects led by Chilean universities, and 6 others involve participation from Chilean researchers. So I think that's organized by universities, PUC Chile and University of Chile in Santiago are the hub of this, and they've actually made a very good job of making a self-sustaining activity. So we look forward to seeing what that achieves in the future. So what I should like to talk about, however, is how science is being changed and the challenges facing science. So that was meant as a sort of to the technologies and to the exciting times in computer science and what we're all doing here. What I'd like to do is give you an overview in the next or so of the challenges in data-intensive science. And I'll start with, one hears a lot about big data. That's a name from marketing departments in industry, and I prefer there is big data, and we'll hear from the astronomers. They're hugely ambitious, looking at petabytes and beyond. But most scientists are actually much more modest, but they have very diverse sets of data. The particle physicists and the astronomers have huge data sets, but they're all of the same character. Here, what we have is in genomics and in environment, we have very diverse sets of data scattered around, coming from sensors, coming from computer simulations, coming from various different types of measurements. And so I prefer to talk about the 4 V's. The volume is one, but there's also the variety. So in genomics, you have, for example, the gene sequences, sequence of letters, then what proteins do these genes express, and what's the structure of the proteins and the pathways. So there's a huge amount of data to put together to find out something that can be useful for human health. And so genomics is an example where we have lots of different types of data, and our job is to actually find, going from data to information to knowledge, information we can act on. This is a picture of Jim Gray in his boat that he was lost in. His boat disappeared in 2008. Just before he died, he gave a talk, and in his talk to the Science Board in America, he talked about the fourth paradigm, and it was based on his experience working with astronomers and other scientists. So this was the first truly large data project in... I'm trying to turn this off. How do I turn it off? I should be able to turn it off, yeah. Okay. It was a very high resolution, you could see the telescope, survey of a quarter of the night sky with images and spectra of over 300 million celestial objects. Now, with 300 million celestial objects, galaxies and so on, there are only 15 million or 15,000 or so professional astronomers. So this is actually where the astronomy community publishes the data before the astronomers have done the analysis. And then that enables the public to help, and there's a project called Galaxy Zoo, which actually allows the general public to help the astronomers classify galaxies and make discoveries. And there have been a number of interesting papers coming from that public partnership with the professional astronomy community. Well, this was a project that Jim Gray worked with, and he, with Alex Saleh, astronomer at Johns Hopkins, with some graduate students, decided to make this data available. So they put it up on one of the first web services, and everybody could see it, everybody could use it, and it's become a great beacon for these new type of ways we do astronomy. And so from that experience, Jim identified that there was a new mechanism for doing science. We've always had experimental science, looking at the heavens since the Egyptians and the Greeks and so on. And in the last few hundred years, we've had theoretical science because we've understood many of these phenomena in terms of laws of nature, which are mathematically expressed. And they're mathematically expressed, so you can explore them mathematically and understand what should happen in a given circumstance, and then you can go and do an experiment to see if that's the case. And that's the way we've traditionally done science for hundreds of years, with theory and experiment, and that's what we train our graduate students. But since 1950, when we invented digital computers, there's another way of actually exploring science. If you want to understand what's happening to the climate, if you want to understand how galaxies are formed, you can't do the experiments. And the equations are too complicated to solve, so simulation is the only way. And so besides the experiment and theory, we now have some graduate students and research faculty who are trained in using computers for algorithms, for numerical methods, for parallel computing, for parallel programming, and all these sort of different types of skills, in addition to theory and experiment. What Jim Gray noticed that we now have a different type of science, where we have now, instead of a relatively small amount of data, we have huge amounts of data coming from many different sources. Captured from instruments, things like high-throughput gene sequencing. Supercomputers generate huge amounts of data from their simulations, and we have sensor networks giving, instead of data at small amounts at intervals of time, we now have data coming in 24 hours a day, 365 days a year. And so we need new sets of tools for analysis and data mining, for data visualization and exploration, and new ways of publishing and making this data so it can be reused. And that's what Jim meant by the fourth paradigm. We need to train students who can handle big data, who know what a schema is, who can push it into a database, who can visualize it. These are the skills we now need to add to the skills we teach our students. You can find Jim Gray's talk written up in this book, along with a collection of essays of scientists with a computer scientist looking a few years in the future as to how the field is evolving. And these are some examples of some of the projects that we've done. These are both available under a Creative Commons license, so you can download it and use it as you like, or you can buy a copy from Amazon for $1. I don't know who gets the $1, right? Because we don't. Right? The other thing that Jim was very active, Jim Gray, he worked with the National Library of Medicine. Now, the National Library of Medicine is very fortunate. It's well funded by Congress in America to create a library that anybody can use. And in particular, they created a thing called PubMed Central, which is not just the abstracts of research papers, but this is a place where all the papers funded by the National Institutes of Health in America, if you get a grant from them, you have to put your paper into PubMed Central. This is the open access movement, and they were one of the first to have an open access policy. And so what Jim liked about this, because in addition to the publications, you can go from the publication to the data that was used to generate that research. And so there's a number of databases in the National Library of Medicine from all these protein sequences, nucleotides and complete genome sequences and so on, where you can actually search these from the paper. You can go from the paper to the data, you can look at different databases, and you can make your own discoveries, add your own data. So this was the model that Jim saw of science in the future, that actually we would be going from the data to the paper. Why is it important? Well, this is just to show you that there really is a problem in research reproducibility. Let's just look at this bottom one here. Studies carried out by Bayer and Amgen trying to reproduce the results of summarized in papers published in major journals like Science and Nature. They found they could only produce 70%. In fact, Amgen tried to reproduce 53 papers in Science and Nature, and they were only able to reproduce the results of 7 of those 53. And that really is a problem for science. If we cannot actually reproduce other people's research, then we are in problems. Now, there are many reasons for that, and it's not typically scientific misconduct, but it is actually inadequate recording of the data, inadequate specifying of exactly what was done. So we need to make it sure that science is more reproducible. And so Jim Gray's vision of the future was something like this. It was modeled on his experience of working with the National Library of Medicine, that you can go from the literature to the data, you can add your data, and you can combine it and write your paper, and then your new data is now saved and conserved. And you can search through all these things. You can make it so it's impossible for people not to know about this research being done. Because in the time I've been working with researchers, I see there's a lot of redundancy. We repeat ourselves. We're not very efficient. And I agree with Jim that we can sort of increase scientific productivity and what he called the scientific information velocity. So that's the challenge. Now, if you're in the National Library of Medicine, in bioinformatics and medicine, you have a budget for producing those databases I just showed you. Of course, in most fields, like archaeology or whatever, you don't have that luxury. We need to make this work in a much more difficult context. Open data and open science. So I think this is important, and this is a slide from a talk that Bill Gates gave in 2005 at Supercomputing, and it just illustrates the fact that publications can be different. Now we have electronic forms. Obviously, you need to be able to go from the paper to the data, and the data can be updated, can change. The documents can be dynamic. You need to actually have the metadata, so you can actually reproduce the research, and you can have different ways of collaboration and also defining the influence of the paper. It doesn't have to be the citation count. There can be other metrics for deciding the influence of a scientific paper. So I've talked about open access to the text of the papers, but in 2003, in the Berlin Declaration of major funders in Europe and the US, they defined open access not only as the text of the paper, but the original scientific results, the data and the metadata. So now funding agencies are not only interested in your paper and what you did, but they also want to know what you did with the data. And this is a meeting in 2013 of the G8 science ministers, and they had an open data charter. They want it usable by all. They believe that releasing the data allows innovation. You can get companies developing products using this publicly funded research data. The argument is if it's publicly funded, it should be publicly available. And there are many other areas, but I'll just take the US to show the trend. So NSF, they now expect investigators to share with other researchers at no more than incremental cost within a reasonable time the data and so on that support the research. So that's now going to be an obligation when you get an NSF grant. The NIH, National Institutes of Health, has also now gone from open access to text and publications to making a statement about the data that you have. Data sharing is essential for expedited translation of research results into knowledge, products and procedures to improve human health. And many governments around the world, and this is the US, data.gov, but there are certainly examples around the world, of making public data available so you can actually have new services, new innovation. So data is going to be very important, and publishing data is a complicated business. This is the Public Library of Science, which is an open access journal, and they have announced a new data policy. So when you publish your paper, they insist you now actually make sure you do something with the minimal data set consists of the data set used to reach the conclusions drawn in the manuscript with related metadata and methods. So data is becoming important. And what is the value at the end of the day? Well, I'd just like to give you two examples, which to me are slightly surprising. They come from the medical arena, and in the medical arena there's a lot of concern about privacy and using other people's data and naming patients and so on. But this is a case where that's been overcome. This is in looking at Alzheimer's disease for neuroimaging, and actually 14 different centers, which typically would have done their own research, published their own data in their own data sets with their own formats and standards and metadata. They've come together and agreed that they will use a common standard of metadata and image format, and they now are making it available publicly in a central database. Now, this to me is remarkable because it comes from the medical arena. And it's interesting that on this ADNI website, several dozen papers have been published by researchers who didn't take the data. So actually, by making the data available, other people can use the data. Another example, which is also in the same sort of area, is for autism research. And here you have many charities doing their own research on their small data samples, and by getting these different charities with their different data sets to agree to put their data together in a common format and to work together, they've now actually been able to get a much larger base of subjects, 85,000, instead of the small ones of each charity independently. And so this is what they call community science. So there really are some benefits if you can actually get the data and the metadata in a form that can be shared. So what's the state of the art of, when you publish your paper, what about linking the data? Well, it turns out that the particle physicists led the way in open access. The astronomers have led the way in linking data to publications. And so this is the Astrophysics Data System, ADS. Slightly confusing because it isn't about data, it's about the research papers. But in their context, they also link to the data, they link to objects, link to the resources. Where is the data? The data is curated and held in Strasbourg in the Centre de Données Astronomiques. And there they have actually got funding from various sources to curate astronomy data sets. And so you can get a picture where you can go from the publications over here to the data here, linking with a variety of tools. We've been working with them on Worldwide Telescope, which I'll say a little bit more later. But you can see this linked connecting the paper to the data is an important concept. This is a slide of Alyssa Goodman, who's a professor of astronomy at Harvard. So how do they do? Well, this is sustainability of data links. These are the volume of potential data links in astronomy publications. What I'd just like to show is that if I take from 2001 and look at 2011, 44% of the links in those papers are now broken. So you can now look at those papers which had links to data in them, they no longer work. So we do need to do a better job, and they're probably one of the leading disciplines trying to link publications to data. So there is a long way to go. So we need data science tools. And in Jim's talk, in this Fourth Paradigm book, he talked about the need in the big projects like the astronomy and particle physics. They have many hundreds of millions of dollars for their research grants, and they have actually a specific amount for doing software development. But the majority of researchers do not have that luxury. They have to use open source tools, put them together in any way that's possible. And they use tools like Excel to manage their data. And we need to make it so it's easy for them to go from acquisition of data, collaborating and visualizing, analysis, data mining, publication, dissemination, and finally, having taken a lot of effort to get this data, you need to keep some of it. If you've got measuring the temperature of the Pacific Ocean off Chile, if you want to know what happened 20 years ago, you need to be able to read the data that was taken at that point. So some data needs to be preserved. So in Microsoft Research, and you'll see examples in the Demo Fest and in the talks, we've been looking at various tools to help the researchers that can interoperate. And one is a tool called Fetch Climate. So we have stored some data sets up in the cloud on Azure. And what this enables you to do is to specify what region of the Earth you want, what data you want, the rainfall, you want the crops that are grown there and so on. And you can run models going from now to 50 years in the future and so on. But it enables you to get the right data for what you want to do in a very easy way. And so that's just an example of how you can actually use the cloud and a tool to help you do the science that you need to do. I talked about Worldwide Telescope, and you'll see a talk about Worldwide Telescope and a demo in this meeting. It allows you to zoom and visualize not only in the visible, but astronomers are very strange people. They classify each other by wavelength, all right? So they're classified as a visual in the visible region, or the infrared, the radio, ultraviolet, X-ray, and so on. And so with the Worldwide Telescope, you can switch from one view to another. You can superpose them and see objects in ways you've never seen before. So it gives you a wonderful way of exploring huge data sets in novel ways. And you can also have experts like Alyssa Goodman giving a talk about star formation. So she'll start off with the infrared data and this particular galaxy showing that they've got young stars forming. Then she'll go to the visible and look at another galaxy. And she takes you on a tour through these data sets. And when you have increasingly complex data sets, actually the ability to show people how you got your conclusions, giving these expert tours and making it possible for you to do one too, is important, and I think will be even more important in areas like environment. So this is what we did with astronomers, and what we did took us 5 years, but we managed to actually make a transfer to the Excel team, and so now you can do some of these visualizations in a standard. When you buy Excel, you can get this capability to visualize geospatial data on the globe, and you can do it in time sequencing, temporal patterns, and so on. And so you can generate all sorts of interesting things. Just to show you a couple of examples, here's showing three-dimensional visualization. I forget whether this is drug arrests in Chicago or something like that. But you can look at all sorts of crime data. You can look at environmental data. And it's called Power BI. BI, it stands for business intelligence, so it's primarily intended as a visualization tools for businesses to see their sales in various regions in new ways and so on. But it also can be used for science. And it came from science, and now you can use these tools as a standard part of Excel to use them in science. So instead of looking at the clouds, the stars, you can also look at the Earth. And we've actually demonstrated a tool called Layerscape, which allows you to look at the Earth and to look at events like earthquakes, which is obviously very relevant to Chile, and especially this region, in new ways. So this is the Japanese Tohoku events, and from this you can not only plot the sequence of the pre-shocks, the big shock and the aftershocks, you can go down underneath the Earth, you can actually see how deep they were, you can fly around your data, you can also do models. This is a model of the tectonic plate. It's a subduction zone, so it goes underneath the Pacific plate, and you can see exactly where the earthquake fits on that, and how your model of how the earthquake and the plates collide, does it stand up to practice? So you can actually do these tours. So I'll show you a little video here which actually shows earthquakes. So this is actually looking at, again, the ring of fire, but this is now the Asian side. This is in New Zealand, which obviously Christchurch was a major event in earthquakes, and you can see the magnitude represented by the height. And so looking at them again, this is looking from 2009 to 2010. You can see this is a very active region. And then going to the other side, you can see up here, actually, we're doing pretty good in Seattle, but we're probably going to get a big one every 200 years. The last one was about 200 years ago. So it's slightly nerve-wracking. And then, of course, down in Chile, you can see this is the earthquakes along the coast, and you can see also the big earthquake that happened in 2010. So it's a new way of visualizing data. Actually, you can do here what you can't do yet in the Excel. You can go beneath the surface. The business applications, they didn't want to go beneath the surface, but scientists might need to do that. Okay, so I talked about Excel, and these are visualization tools in Excel. Another one of the things we've been doing, many scientists store their data in Excel spreadsheets. And if you go and pick up that data a year or so later, what was actually done to it, you need to be able to record what you did with it. And so this is something we did in collaboration with the California Digital Library for an NSF project. It's called Data Up, and it's an open source add-in or a free service you can do from the cloud, which actually enables you to add metadata to remind yourself what you did to the data and what the calculations are. And we have Chris Toll, one of the team who developed this, who is here, can tell you more about such tools. Okay, I should finish fairly soon. The role of the cloud. I was talking to the Minister of the Economy just before this talk, and one of the things that I think has changed from when I used to be a professor in a university, I was Dean of Engineering, and one of the things was actually helping the staff who wanted to do spin-outs and startups, help them do that. And I think the cloud helps that because they don't need to actually go and buy large numbers of resources. They can rent them from the cloud. So this is what Microsoft has, and actually there are now, besides Amazon, Google, Microsoft, and so on, these are some of our data centers, but there are now Microsoft data centers in Latin America, so I need to update my slide. But you can see they have big data centers with hundreds of thousands of processors. We've improved our energy efficiency as we've built new centers, and we've got better at packaging and building these data centers to be energy efficient. And they're also linked by huge amounts of bandwidth to get the data up there, to get the data back, to access these processes. So this is the sort of, a quote from The Economist, data centers have become as vital to the functioning of society as power stations. And I think that's probably no exaggeration. So I'd like also to introduce one other thought here. This is, as you can see, this is a Windows phone as opposed to an iPhone. Here you talk into this and you get speech recognition, but there isn't enough processing power on this device to do the speech processing quickly. It's done up in the cloud. So it goes up into the cloud, it does the calculation, comes back to you less than a second. And so it turns these devices, if you like, to portable supercomputers. You have access, as long as you have an internet connection, you have access to huge amounts of computing power and stored data just from a mobile device like this. So I think that's another reason why I think the cloud changes the game. We're actually looking, I talked about this data cycle. One of the things we're working with are these data repositories. Now, you don't necessarily have to have a large amount of data stored locally. You can have some locally and some in the cloud, or you can have it all in the cloud. And these are some of the projects that we're working with to put data repositories in the cloud so that universities can afford to do these, store their data. Because I think it will be increasingly important and increasingly necessary for universities and university libraries to play some role in storing data for their researchers. We also have a program which you can, there was a workshop, just a training session just before this conference about how you use the cloud, how you use Microsoft's cloud. And so there's now a very simple way for applying for time, and you get a large grant of cycles and storage to do some serious science. And you can see whether the cloud is useful to you. And this is a easy thing to apply for. We look at applications every 2 months. It takes 2 or 3 pages. That's all you need to put in. So if you're interested, this is a way you can experiment and see how the cloud could be useful for your research. So to conclude, data science in the future. Data science, of course, is used by industry to mean business intelligence. Here I'm using it in a broader sense to talk about scientific applications. If you look in your favorite search engine for the term data scientist is the role of the future, the hottest job you haven't heard of, the new hot gig in tech, and so on. So it's a very exciting time in industry. They're looking for data scientists. So what does a data scientist actually do? Well, this is one way of categorizing that. There's a data engineer. They're the people who actually make sure that the data comes from the sensors and gets to the right place in the right format, and really work close to the data as it comes in from the satellites, from the sensor networks, or whatever. And then there's the data analyst who use advanced statistics and analytical methods and visualizations to get some understanding of the data. And so they actually, all they want is large amounts of data, which has had some processing on it to make it usable by the data engineer. And finally, there's another class of person who is actually concerned with actually preserving that data, making sure that you can still use it 10 years from now, 20 years from now. You're not going to store all of it, so what data do you want to store, what don't you want to store? A data steward, curating and preserving data. And so really what a data scientist is being asked to do is what a webmaster was asked to do in the original times. You're asked to be Superman, all right? So you want to do all of these things. And obviously nobody does all of those things. So there are actually going to be subdivisions where people specialize in certain parts of this skill base. Why is this useful? Well, we know we have earthquakes in Chile, and we had one not long ago in northern Chile, and we had one in the south in 2010. But you also have, increasingly with climate change and global warming, the possibility of forest fires and bad fires driven by high winds and so on. And in Valparaiso, there was a tragic event very recently. So the question is, can you do anything about that? And one of the projects that you'll hear talked about tomorrow is a project stemming from the very bad fires that took part in Greece in 2007, when 50 people died and thousands of buildings were destroyed. And in particular, Greek islands are particularly vulnerable because a bad fire on a Greek island could wipe out the whole island. So one of the projects that they did, the Microsoft employees who were Greek, along with researchers at the University of the Aegean, and you'll hear Nikos tomorrow talk about this. They looked at the island of Lesbos and actually took all sorts of data into account. You have to have the real-time weather forecast, the satellite pictures, the simulations. You have to have the topography of the island, what the vegetation is, whether it's forest or crops or urban, where are your emergency vehicles, and so on. And so you want to be able to have to the fire chief, who's actually trying to keep fires down to a minimum, to have on his dashboard every morning, if a fire starts here and the wind's coming from here, what are the most vulnerable areas? Is it likely to happen? Is it not likely? And so to do that, it's going to take a lot of computing. Well, using the cloud is a way of doing that, because on the Greek island you don't have a supercomputer, but you do have the cloud access. And similarly, getting all sorts of different types of data, and then using very sophisticated techniques to give you the probabilities for these different predictions. So that's being talked about. And I think that's a very relevant example for many disaster recovery areas, and that's a theme of this workshop, and you'll see other examples here. But I'd just like to leave you with the thoughts of the technologies that come together to make such predictions. And they are big data, so you have to have data sets which are very large. You need very sophisticated analytic techniques to be able to get meaning from that data, and the cloud to do the computation that you need and to store the data and so on. And that enables you to make informed, intelligent decisions about what to do, where to put your resources, where to put your fire engines, and so on. So it's a very exciting time for computer science. I think the computer science technologies have wide application in many areas of science, in health and in environment, and indeed in education. So I look forward to learning more at this workshop, and I thank you very much for listening. Thank you.
¿Preguntas? ¿Una pregunta allá, por favor? Sí, adelante, por favor. Micrófono, por favor. Sí, va a haber uno a cada lado micrófonos para que, por favor, estén atentos.
This is a simple question. Is Microsoft doing some research with respect to the grid? CERN, with the grid, I mean, with CERN and all that.
Well, you say the grid.
The grid, I mean, the distributed computing, which is
okay.
kind of
Okay, so the grid, I worked for 5 years on grids.
Yeah, that's right.
And also with CERN. I used to be at CERN for a couple of years.
I know.
All right, very good. They still buy my book. In fact, it's stolen regularly from the library.
I have your book.
Well, I think that the grid is fine. This is where people share resources. So, you know, scientists, particle physicists are very happy to share, and so they'll allow people to use their cluster if they've got spare time. I think that's very specific to particle physics, where they have these big collaborations at CERN with over 1,000 researchers. I don't think that's so typical to use, and so I think that the cloud is a much better, a much easier example of a shared resource that you can get and people can share data and use. So I think for most subjects, the cloud is a better way of doing this resource sharing. But the grid is certainly possible for particle physics, and it works just fine. Yeah.
Otra pregunta acá.
Thank you very much for your talk. I'm a computer scientist. I'm not a data analysis. So I feel a little bit afraid of putting all my data there because of consequences that I don't know about the data that I'm putting there. How to prevent to put information that maybe is private or maybe is sensible from our country or from your own research?
No. The question is how safe is it to put data that you really may care about in the cloud and how it can be accessed? Well, I think you need to look at service level guarantees is one thing. I think that Microsoft does a pretty good job in terms of security, but nothing's perfect. And so there are options that you can keep some data locally and you can keep some in the cloud. I think for most people it doesn't matter whether it's, if you're in England, for example, the data centers in Dublin, in Ireland. So most of the data, but the government may want not to have some data there, so it may want a private cloud for it doing its own data. And so some companies and some countries certainly will want that. And personal information, I think it's as safe as anywhere, all right, because you've seen all these recent security scandals in companies and so on where the data's been hacked. It's not unique to the cloud, right? So I think that you should be reassured, but you should, look carefully and make sure that it satisfies what you want, all right? So I would suggest you have a try. So yes, and I'll come back to you. Yes.
Thanks. Well, I've seen that, unfortunately, today we are not so close to get open data for everyone in science. For example, in astronomy, you can have a lot of data from all those catalogs you showed, which are open for everyone. But if you want new data from upcoming surveys, you need to apply for time, and you need to guess. You need to get telescope time. Then once you get it, you have this data and you don't want to share it with everyone, right? So many people, they have their own data and they keep it private for at least 6 years in order to get some advantage in the research. So this is unfortunately happening in many, many fields where people do not really share their data, and you only can see data when it's already old and it's not so interesting. So how you think that this could be improved by maybe government or something?
Well, first of all, I think it's perfectly reasonable that if you've taken the data, you get a period of time to analyze it, all right, without having to share it, because you may not have the data all sorted out. You may not have found the biases, the various types of errors in your data. You want to make sure you've got it right, and then you want to publish something. So that seems to me totally reasonable. Now, whether that's 1 year, 2 years, 3 years, or 6 years, that's not so clear to me. You'd have thought that it would be something more than 1 year and less than 6 years. But I think that depends on the funding agency. I think they can change that, and they need to take the advice of their constituency. Right? It's not something that should be dictated from outside, and I think it will vary in the. What I know about are the science and engineering disciplines, but in the arts and humanities, for example, which are increasingly digital, they have a very different way of publishing, and it's a longer time scale, and so things differ from field to field. But I think it's absolutely a concern. But what I don't like to see is people say who've had the data for 10 years and they won't release it. They regard data mining as data mining, all right? And that's not what they should be doing. They should be actually, after a certain period of time, they should be made to share it. And they'll say, well, they won't understand what's been done to it. Well, they need to actually annotate their data with metadata. And the only way you'll get them to do that in the end is by sanctions. So on open access of NIH, initially when it was voluntary to put your paper in, if you got an NIH grant, it was 20% of the people did. When they signed into law by George W. Bush, so they had to do it, it went up to 70%. Last year, the NIH said, we will not give you your next grant unless you put your papers in. It is now well over 80%. So you need to have some sanctions, and that needs to be worked out with the community and the funding agency. It should certainly not be dictated by Microsoft. Right.
Coming back to one of your first slides, you showed us that there are many scientific applications in which you can use cloud computing to conduct scientific research. But on the extreme of your distribution, there is the the high demand for scientific, for high-performance computing facilities. Do you see a future in which high-performance computing can be accessed through the cloud?
Okay, so the question was, there is a lot of computing facility in the cloud, but I mean, I used to do parallel computing, so it's what they used to call embarrassingly obvious parallelism. You want to run the same model with different parameters. You can do it on different machines, and the more machines, the more parameter sets you can do. So much of the parallelism that people use is like that, but not all. If you want to run a computational fluid dynamics code, which requires close coupling of the processors, because you split the whole domain up across these processors, and you have to exchange data between them, you need to have low latency, high communication bandwidth between the nodes. So it is possible to do high performance computing in the cloud, in Microsoft's cloud and in Amazon's cloud. I'm not sure it's perfect. In fact, I'm sure it isn't perfect. And it certainly doesn't go up to supercomputer levels like petaflops. So if you want supercomputer levels, petaflops, go to a supercomputer center. But the cloud, for most people, they don't want petaflop computers, but they may need some high-performance computing. So I personally think it's a very interesting area, and one that I personally am very keen for Microsoft and others to pursue. But another of the problems is that you may use MATLAB, and you then want to use MATLAB on 128 nodes. Well, what's the license for that, and how do you pay for that? And so there are all sorts of issues of third-party software which make it rather complicated. But I think something can be done, and I think for reasonable scale, high-performance computing, closely coupled MPI codes, I think you can do something. But I don't think it's perfect yet. But tell me how you get on. Try it.
La última pregunta, por favor.
Good afternoon, Tony. If everything in the future were contained in this cloud, what happened if this cloud failed?
Okay, that's a good question. If you put everything in the cloud and the cloud is burnt down or earthquake destroys it, what happens? Well, first of all, when you store something in our cloud, you get 3 copies. You get a redundant copy in the same data center, which isn't much use if that data center gets burnt down. But you get another one in another data center. But you can pay less and only get 2 copies. No, I think it's a valid concern. And I think that what we're seeing we're working with the Environmental Research Agency in the UK, and they are looking at a hybrid solution where they keep some data locally and some in the cloud. But I think you do need to be mindful of that, and you need to have a strategy to do that. When I used to run the Electronics and Computer Science department, I instituted a policy where we had a serious policy for what to do about data. So you have to have a store of the data which is not in the same building. And then the building got burnt down. So it actually was worthwhile. So I think you do need to worry about these things. But I think the cloud does give you a solution, which means that you can have a local copy which may get vandalized or whatever, but there could be a copy kept in the cloud or one of the data centers. So I think it gives you more options, and you have to choose the one that works for you.
Thanks.
Sí.
Thank you.
Por favor, acompañemos nuevamente con un aplauso y despedamos a Tony. Y ahora paso nuevamente el micrófono a Sergio.
Thank you very much for listening. You were very patient. Thank you.